to be the last calculus specific thing we do in this class, the particle in the box quantum problem. So we're going to spend the rest of our Tuesdays looking at this. And I know Chad's like, really? Because Chad knows this one inside and out. So if you ever have questions on it, go see Chad. So in class last week, we separated our Schrödinger equation, or we said it's possible to separate the Schrödinger equation into a time-independent Schrödinger equation and a time-dependent Schrödinger equation. So we have two different equations. Now, we have to back up a step because I'm guessing, except for Chad, who, like I said, has had this inside and out for the semester, you might be forgetting what the Schrödinger equation is. So can you remind me about the Schrödinger equation, where it came from, why it's important? Yeah, I know Chad knows the answer. I'm not looking at him. Chad's had this question on test, maybe twice. Just tells you how important it is. No recollection?
Is it how time relates to how time can be independent?
Well, the last step we did was to separate them. So that is an important step along the way. But the origin started with De Broglie. Now, we talked about De Broglie in class yesterday, right? And his saying that light can be a wave or particle, so maybe a particle, like an electron, should be able to be a wave as well. And then Erwin Schrödinger got excited about this. Peter Debye kind of challenged him, and he came up with a wave equation, an equation that's based on energy conservation that allows you to find, just like you have a wave equation that allows you to find an electromagnetic wave, we have a wave equation that allows you to find a matter wave. So this is working just like the wave equation for electromagnetic waves that came from the four Maxwell's equations that we went through before. And so just like, remember, with the electromagnetic wave, using the wave idea, the probability of finding the particle of the electromagnetic wave is proportional to the amplitude of the wave function, as the electric field function, squared. And so we have this wave equation that finds an amplitude that's analogous to electric field. And if we take the square of that, that tells us about the probability of finding the particle. And somebody might say, well, wait a minute, but an electron is a particle, whereas light is not. We're saying they can both be a particle or a wave. It's correct to call them either one. And so this here gives us the time variation function for the amplitude. So how the amplitude changes in time. And this gives us the spatial relationship, how the amplitude changes in space. So for instance, if we're talking about a wave on a guitar string, the wave on the guitar string has, in space, you have a node at the ends, and then you can have an antinode in the middle, or you can have a node in the middle with two antinodes, and so on. That's the spatial relationship. But then you have the time relationship. If you have something like this, in the places where you have the antinode, it's going up and down in time. It's not stationary. So you have the two separate. This one here is how it's changing time, and this one here is telling you about the maximum the amplitude can get. So we have the same type of thing. This top one here, that's the one we're going to work with. The lower one, I would be willing to bet you that on most days Chad wouldn't remember it because that's how much we use it. We know it's there, and so the solution for that is very simple. This equation, if we want to solve that, we've been doing this since the first day of the semester. Do you remember doing this the first day of the semester? I see that grin on Michael's face. Yeah, really? I'm supposed to remember the first day. That was the first day of first semester, I might add. I'm supposed to remember the first day of first semester? Yes, yes. Remember everything forever. Steel trap minds without rust. So we have two variables here. Now, the scary part is identifying what the variables are. but the fact that you have a derivative helps you. What are the two variables in that equation? Phi and t. So if we have two variables and we want to solve it, what did we have to do? Bueno.
Okay, that's all I have to do today.
Yeah, I'm done. I did my part. And so I'm going to take this and separate the variables. So I'm going to multiply both sides by dt over IH bar. At this point, we should be comfortable with H bar because I introduced it yesterday in class, right? Introduced once, forever comfortable. Is that the way it works? Yeah, a couple times maybe. So what is H bar? H over 2 pi. And that is the value for H that we use in quantum mechanics pretty much exclusively. We use H bar. So given this relationship now, multiplying both sides by dt, I'm going to have, and dividing by IH bar, we have d phi is equal to E phi dt over IH bar. Now I have t on the right-hand side, but I still have phi on both sides. So how do I get phi by itself? How do I move phi to the left-hand side? I know. Trey said he's done. He's already given his significant input for the day.
Divide by E.
Yeah. I need to get my phis together on the left side.
Okay, so you have to divide.
So those cancel. Now I have d phi over phi equals this. Or as we like to write, minus IE over H bar. Because we don't like to have the imaginary number in the denominator, we like it in the numerator. And because I is equal to the square root of -1, that's the definition of the imaginary number I, then I squared equals -1. So if I multiply top and bottom here by I, on the bottom I have I squared, which is -1. That's how I have minus I. So now when we look at this, I of course forgot to write my last thing, dt. That's pretty significantly important. The left side is a function only of phi. The right side is a function only of time. So I should be able to integrate these independently. And I'm going to do something we never do in physics, an integral without limits. Well, yeah, I know. I didn't even know that existed, right? I'm in physics class all year. So if I do that, what's the integral on the left-hand side? And what's the integral on the right-hand side? Plus c, right? Plus constant. I do this so rarely. I've got to remember these things. Okay, now if I want to solve this for phi, I'll take the inverse function of natural log. What's the inverse function of natural log? E. So I do the exponential. And I have that's a C. It looks wrong, but it's a C. So there's my equation for phi as a function of time. E to the C is just a constant, so I could replace E to the C with D or A or whatever I want, because that's just a constant. So I'm going to put equals A E to the minus I E over H bar T. So that's my equation. And what is A? Chad? Normalization constant. He's been doing a lot of that too. And right about now, he's probably realizing, wow, it would have been a lot easier to have started having this stuff covered. So that's our time-dependent variation. What is that? Well, if you use the Euler relation, and I've run out of space, we use the Euler relation, that is it's a sinusoidal variation. Now, our constant is going to have to be such that we get well, actually, it doesn't have to be real. So, but this is our relationship that we got. So that's how it's going to vary with time. Just like a wave on a string varies sinusoidally as it goes up and down, right? And so we know we will always have this to multiply our solution by to get time dependence. And so since this is always going to be there, that's why we ignore it. It's always there. So we just have to remember it's always there and not forget. So now we get to the real problem. This leaves the time-independent Schrödinger equation. And we're going to find what we call stationary states. The stationary states are the states with quantized energy. Stationary, at this energy we have this state, at this energy we have this state, and so on. We're going to find, this is where quantum physics becomes quantum physics. We're going to find as we go through a realistic, not a real, but a realistic problem, that quantization naturally occurs from the mathematics. And at this point, Chad has learned where the principal quantum number for a hydrogen atom comes from, where the two of the other three, we have one more quantum number. They come from the math that follows here, looking for these stationary states. So here is the problem we're going to spend the rest of the semester on. We are going to take a particle in an infinite well. What that means is I have a box, and I remember potential energy, the reference point is arbitrary. And so we say the bottom of the box has potential energy of 0. And then the walls go up infinitely high. And so if I put an electron in this box, what is the electron going to do?
It falls to its lowest state.
Okay, naturally fall to its lowest state. That's going a little ahead of actually what I was looking for here. If I put the electron in a box, just think about putting a ping pong ball in the box. What's the ping pong ball going to do?
It's going to go down.
It's going to go down. It's going to be in the bottom of the box, right? And it can be anywhere in the box. And if I give it some kinetic energy and there's nothing to take it away, right? We have nothing here to take away energy. It'll rattle around in the box. Can it get out of the box? Why not? It has infinite potential barriers. So that means the kinetic energy would have to be infinite to have enough energy to get past it. So it's stuck in the box. It cannot get out. So this is somewhat realistic. If you made this box so it had finite walls instead of infinite walls, then it's realistic. And that is the continuation of this problem that we might get into if I go fast. I don't know how many times I've gone fast in my life, but if I do, then we can lower the walls and see how that changes things. So now I have two things. I have my condition of this infinite well or box with infinite walls, and I have the Schrödinger equation. When you look at it, it seems like this is no way to start a problem. But this is all we have to start the problem. Everything else is just math. So I leave it to you, right? I'm contemplating if I should put Chad on the spot and have him lead through because it'd be good practice for him. But we all know that he's not going to remember every step right? It's the way human life works, especially if you're up front and on the spot. But the first thing I'm going to do is insert this potential function and have three different Schrödinger equations, one for region 1, one for region 2, and one for region 3. So in region 1, That means x is less than 0. I'm going to have v is equal to infinity, so I have minus h bar squared over 2m d second psi dx squared plus infinity psi equals e psi. I should make my psi's look the same. I've been writing in script and then I wrote in block form. So this is my equation. We kind of have a problem. How am I going to have something that is infinite times psi is equal to something not infinite times psi?
Because the other thing.
Because the other thing. The only way that can happen is if psi is equal to 0. So in region 1, psi has to be 0 because that's the only way I can make this equation true. Now let's go to region 3. Why to region 3? Because it's the same. Cutting right to the chase, psi in region 3 is equal to 0. Now we want to find psi in region 2. In region 2, what is the potential energy? 0. So my Schrödinger equation is actually the simplest there.
That's an A, right?
Yes. Yes. Sorry. I'm changing a few characters because I realize they're hard to read. All right, so how many of you are in differential equations? Go ahead. The answer is 0. This is a differential equation. This is why differential equations is really necessary for quantum mechanics. If you're a physics major, you're going to have differential equation before you take quantum mechanics, so you actually know how to find these solutions. But none of us, well, I take physics or differential equations. So what we do for students at your level is we tell you this has a solution with the form psi is equal to e to the bx. So if psi is equal to e to the bx, then what is the derivative of psi with respect to x?
B to the BX.
And what's the second derivative?
B squared to the B.
So if psi is e to the bx, then the second derivative of psi is b squared psi, which makes this easy. I have psi in region 2 equals e to the bx, and the second minus h bar squared over 2m times the second derivative of psi, which we said is b squared psi, is equal to e psi. Now, in order to solve this mathematically properly, I am going to move these so that they are on the same side, the equal sign. So I'm going to go ahead and move this over here. So I will have e plus h bar squared over 2m b squared psi equals 0. Right, since that was negative, I made it positive. I moved to the other side. There are two conditions that would make this true. What are those two conditions?
If psi equals 0.
Okay, psi equals 0. We call that the trivial solution. Trivial solution because how much work did you have to do? None. You said, okay, if that term's 0, but then what do we have? We have no wave function, which means we don't have a particle in the box. So we throw that one away because it means no particle. This is what we would have for an empty box. What's the other solution, the one that's not trivial?
E equals h squared, b squared.
Well, you've got the minus sign.
Oh yeah, neither one is negative.
It's B that I'm looking for, by the way. So I'm going to have if E plus h bar squared over 2mb squared equals 0. So solve for B. Because remember, B was an unknown parameter for the form. And so now we're going to find what B is. And so we have, if I solve this for B, I'm going to subtract E from both sides. Then divide by the stuff in parentheses. Notice on the right-hand side, I multiplied by the inverse. That's still divided by the same thing. And so I have b squared equals negative 2me over h bar squared. So if that's the case, what is b equal to? And we have to be pure mathematicians here.
Square root of 2me.
Now, since my potential energy is 0, my total energy has to be greater than or equal to 0, which means that now there's an error here that I'm sure Chad has already recognized. I am having a square root of a negative value then. What do you do with the square root of a negative value? Yeah. You're supposed to say, can't do it, we got to go home. But imaginary number is the right answer, right? The answer we had up until we learned about imaginary numbers was you can't do that. Okay, what did Nathan forget that almost everyone forgets?
Plus or minus 5.
You have 2 correct answers. And so we define K, that 3 lines means divided or defined, as square root of 2me over h bar squared. And so this minus sign is going to give us b is equal to plus or minus ik. So how many solutions do we have? 2. So that means my solution, I had the form, now I have a better solution. It's going to be a linear combination of the 2 solutions. There's the 2 solutions. So my psi is a linear combination of them. So I'm going to say it's A times the first one plus B times the second one. Now this is a perfectly correct solution. We have some unknown parameters, but it's perfectly correct. In some cases, we leave it like that and we go on. In other cases, we use the Euler relation. Remember the Euler relation? I just wrote it on the preceding page. If that's e to the ik, what is e to the minus ik?
Negative cosine and negative sine. Oh, wait.
Not quite. Go back to trigonometry last fall, a year and a half ago. You learned about these functions, and cosine is an even function. It's symmetric about 0. So if I put in minus k, cosine of minus k, I forgot the x. That's a little bit important. And by a little bit, I mean it's vital. So cosine of minus kx is the same as cosine of plus kx because it's even, it's symmetric. But sine is anti-symmetric. It's an odd function, so that's going to be minus I sine of kx. So if I put those into this solution, oh wait, that was supposed to be cosine kx. Combine those, that's equal to a plus b cosine of kx plus a minus b I sine of kx. So I just have two constants. These are two different constants, but they're linear related to the original. So I'll call this here c times cosine of kx plus, and I'll call this the a minus b times I kx. And this is sine region 2. So that's another option. Both the two equations in boxes are correct, but one's going to be easier to work with than the other, almost always. And in this case, because I've worked this problem literally hundreds of times and done it correct literally tens of times, I know that the second form is going to be the easier one. So what have we done so far? Right? I've been doing a lot of writing and talking. What have I done?
Trying to approximate an energy level of particle in the box or whatever it is.
I haven't even gotten to energy level yet. But what I have done is I have taken the wave equation, the Schrödinger equation, in this case, specifically the time-independent Schrödinger equation, to find a wave function. That wave function is analogous to the electric field function for an electromagnetic wave. So this is the wave function for a matter wave for my particle. And so I found that the function that fits this equation, outside of the box, it was 0. And inside the box, it's this here. Now, it feels to me like I've done something reasonably sophisticated here. But as you might have guessed from the time frame we're spending on this, just getting started. What good is this? What kind of information can I get out of this? You're not really sure, right? Okay. What we're going to find is, first of all, the probability of finding my electron at different places in the box. That's what we're going to find first off. And then we're going to do some other things after that. But I'm not done with this yet. I have found a solution, but you know what I didn't do? I didn't come back and look at my box and look at the boundary conditions. Boundary conditions are the conditions that are imposed by my situation. So for a wave on a string, a guitar string, I had boundary conditions. At the ends of the strings, what condition did I have? I had to have nodes. I had to have the amplitude is 0. Well, in the case of quantum mechanics, it actually is the same boundary condition. It's just we didn't talk about it carefully as where it came from. We just said they're fixed, hence its nodes. But for quantum mechanics, we have a boundary condition. That's a B. that says that psi is continuous. That means that I can't have my wave function go like this. It has to go in between, and except for in cases like this where we have an infinite potential, it also has to be smooth. In this case, it doesn't have to be smooth. In fact, in this case, it's not going to be smooth. It's going to go like that. But psi is continuous. So where are my boundaries in this situation?
Is it 0 and L?
0 and O. I said A. I should have used L instead of A. Depending on what textbook you look at, you have A or L. It's almost always one or the other. And so those were the only places I have to worry about it. So I have two boundaries. Boundary number 1, x equals 0. So at x equals 0, I had psi in region 1 of 0 has to equal psi in region 2 of 0, because it's a boundary between psi 1 and psi 2. So what did we have for psi 1? It equaled 0. Come back here, Trace had said, well, actually, it wasn't necessarily Trace. It was a different place where Tracy said 0. You might have said it here too. But we had psi 1 has to be 0. And so that's just going to be 0 equals. And then we had c cosine. If x is 0, then that's going to be cosine of 0 plus d sine of 0. Okay, you guys are all reasonably good at trig. What is cosine of 0? And what is sine of 0? So that means this is equal to c. Hey, look, what did I just find? C equals 0. So that means my psi 2 is just simplified. It's now psi 2 is just d sine of kx. D can still be anything, but c had to be 0. That's why the sinusoid was easier in this case. So now we go on to boundary 2. X equals L. What am I going to have for my boundary condition now?
Psi of 2 L. Psi of 3.
Yep. It's still at L.
Oh, so L.
Because this is the boundary at x equals L. But this is what you were thinking, psi of 3 is equal to 0. And psi 2, d sine of KL. How can this be true?
So sine of KL would have to be 0.
Or the trivial solution. Or d equals 0. But if d equals 0, we're back to psi equals 0, the trivial solution. So we, again, throw away the trivial solution. And now we have our quantum condition. Sine of KL equals 0. That means k can only have certain values. What is the argument for sine? I don't know why that changed to... What is the argument sine has to have if its sine of this is equal to 0? Okay, it could be 0. It could be pi. So it equals n pi, where n is an integer. Now, I had a student write on my I post my quantum lectures on Facebook so people can view them. And a student after watching one asked, why can't n be 0? Because I just said n is not 0. I didn't say to you, I said in that lecture. So now I'm saying n has to be a positive integer. Why can n not be 0? If n is 0, then that means, of course, k is 0, which means sine of kx is always equal to 0, which means I have the trivial solution again. For me to actually have a particle, I can't have n equals 0 because that would say no particle. Now, why can't n be negative? N can't be negative because we have already taken into account a solution with a plus ikx and a minus ikx. If we put in negative n's, we're just duplicating because we already have that in our solution set. So that's why the n's have to be positive integers. So now if n is a positive integer, then I have kl is equal to n pi. What good does that really do me? It does me a huge amount of good. This is an important question. What good does that do me?
Does it tell us the value of it being quantized?
It tells me the quantized values for energy. Since k was the square root of 2me over h bar squared, then I can just put that in here. Square root of 2me over h bar squared times L is equal to n pi. E must only have specific values now because it's based on n. And so we solve this for E. So if I'm going to solve for E, I'm going to square everything. And so I'll have 2me L squared over h bar squared equals n squared pi squared. I'm going to put a subscript of n on the E now because E is going to depend on n. So to get E by itself, I'm going to have to multiply both sides by h bar squared over 2ml squared. And what I end up with is, and because this is the last step, I'm going to make it fit on this page. E sub n is equal to h bar squared pi squared over 2ml squared times n squared. That's quantum physics. Now I have only certain energies that the particle can have. By the way, you might notice that I did take away that first problem on the homework. Depends on when you did it, if you saw it or not.
Okay.
Yeah, I realized.
Because I didn't know.
Yeah. That problem was the harmonic oscillator, which is a higher problem than this. The second major problem that Chad had to do. And so that's why I took it away. It's not something we talked about. But now we have quantized energies, only specific energies. And we have the actually startling outcome. What is the minimum energy I can have? N equals 1. So it's h bar squared pi squared over 2ml squared. That is not 0. When I was asking about what's going to happen when I put that ping pong ball in the box, the particle in the box, Michael said, well, it's going to go to its lowest energy state, right? It's going to try to. In this case, it goes to its lowest energy state. It's not 0. You absolutely cannot have a particle at rest in a box. It's always going to be moving. That's a result of quantum mechanics. That's not what we see in classical physics. Yeah.
So does this kind of go back to like when we were talking about microscopes and the it's moving? Is this what it is? Because there always has to be energy in it, so it always has to be moved to even the slightest.
It a little bit different if I remember. Are you talking about Brownian motion or something else?
Yeah.
That is a classical physics thing. That's we did the.
But I mean, would this be an actual explanation for why? Because they didn't have a great explanation.
No, the explanation for that is the kinetic theory that we went through that said that, for an ideal gas, the temperature is proportional to the average kinetic energy. That's what that is specifically related to. And now we get to a very odd thing about what absolute zero means. Because absolute zero is when you have everything in the lowest possible energy state. And we always say when things stop moving. But quantum physics says, unless your molecules are free to move everywhere, that they're going to have to be moving. They can only come to rest if there's no boundary. Because where did this come from? It came from applying our boundary conditions. If there's no boundary, yeah, they could be at rest. But if there's a boundary, they can't be at rest. And so absolute zero doesn't actually correspond to a cessation of motion. And so I always try in class to be clear on that, but it's just kind of confusing because, you say the temperature is proportional to average kinetic energy. Shouldn't it go to zero? And average kinetic energy can't go to zero if it's bound. So that's a really important outcome. And I might pick up here. So let's see for us. So using a time-independent Schrödinger equation to find the solution set, we have this set. Oh, actually, I went farther than this slide took us because this only goes to having the constants. And here's the linear combination that we made. Remember going through the math of showing that these two were equivalent? And then we applied the boundary conditions. So we've gone to the next slide after this. So now we have our solutions. Now this here is something we did not do. So let's go ahead and do that. Another thing, normalization. And to get what normalization means, we need to start with something that's already been said in general physics, but that I haven't reminded you of today. When we talked about a photon, we said the probability of finding a photon in some region dx was equal to the electric field squared dx. Do you remember going over that in class? Well, since the electric field was our wave function for electromagnetic wave, for a matter wave, it's still got to have the same relationship. So the probability of finding a particle at some point is psi, we say here mod squared. Mod is short for modulus, which means the complex conjugate. And you guys probably haven't done too much complex analysis. Complex conjugate, psi star's complex conjugate means all i's become minus i's. That's what complex conjugate means. So when you do this mod squared, you're taking psi star psi dx, and that is always going to give you a positive real value, which is kind of important because if that's the probability of finding something can't be negative. Yeah, chances of me winning the lottery is -1. No, that doesn't make any sense. Chance of me winning the lottery is approaching 0 from the positive side. It's, different meaning. So that's the probability. What's the probability? If I put one particle in the box and then I check everywhere in the box, what's the total probability of everywhere in the box if I add it up? 1. We call that normalization. Normalization means the sum, I'll put it in English instead of math, sum of probabilities of finding the particle in all space equals 1. And that makes perfect sense, right? If I have one ball in the box and I search everywhere in the box and I say, what's the probability here, 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 here? Add them all up. I better come to 1. And so that's what we call normalization. Now, for a continuous distribution, how do we sum?
Do it divide in sections.
Say what?
Divide in sections.
If it was discrete, if it's discrete, we do that. We divide it into sections. If it's continuous, those divisions have to become smaller and smaller until we have taken integral. So, well, we take the integral from minus infinity to infinity, so we're covering all space of psi star psi dx. Now, in this case, I had 3 regions, so integral from minus infinity to 0 of psi 1 star psi 1 dx, plus the integral from 0 to L of psi 2 star psi 2 dx, plus the integral from L to infinity of psi 3 star psi 3 dx. That's my normalization. And what does that have to integral, my normalization integral, and what does that have to equal? 1. Now we can simplify this. Because what is psi 1? So that's 0. What is psi 3? So we have a simpler integral. 1 is equal to the integral from 0 to L of psi 2 mod squared psi 2 dx. Putting in our psi, so there's, let's change the color. In red, I have psi star. Go away. And then in blue, I'll put psi. So there's my normalization integral. D star D, I can simplify that by calling D star D D mod squared. It's a constant. So now I need to do this integral. Who knows what this integral is? Here's the easy way to do it. Sine squared of ax is equal to 1/2 of 1 plus sine of 2ax. See, I do that ways. And it's got to be cosine. And it's got to be minus. Because sine squared of 0 is 0. And I need it at x equals 0 to be 0. That's where I said 1 minus cosine squared of 2ax. So if I integrate that, I'm going to have a constant of 1/2 minus it's not cosine squared anymore, it's cosine. Yeah, it's my mistake. Cosine. Yeah, it makes a difference. Otherwise, what did I profit myself? Not very much. And so this here is a sinusoid, and it's going from 0 to L, so I would have from 0 to n pi for my arguments. But if I have 2, then I'm going from 0 to 2 pi, 2 n pi. Well, 0 to 2 n pi means I'm doing a complete cycle or 2 complete cycles or 3 complete cycles. What's the average of cosine over a complete cycle? 0. So that means, and I mean, I didn't look this up, but it has to come out like this because it just has to. And so the average when I do the integral of cosine of 2 n pi over Lx dx, that's going to give me 0 because I'm going from 0 to L. So I'm doing an integer number of cycles. I'm taking the average for an integer number of cycles. So that's the hand waving way of saying this is equal to d mod squared times 1/2 dx is just 1/2 L, going from, therefore d mod squared is equal to 2 over L. So d is equal to square root of 2 over L. And technically, you could have times e to the I phi, where phi is any angle. We just go ahead and choose phi to be 0, and then it's just 1. So we arbitrarily choose to just drop that off because it could be anything. So that's where that square root 2 over a, and here notice I changed from L to A, L and A to be consistent. So that's my solution. I will pick up here next class period. And so next class period, we'll be talking about what does this mean?